here's what you're trying to prove. That H is in fact this. Okay? In other words, A is your generator, A is of the form G to the little m. Alright? So if we can prove that, we're home. Because if A is the generator, that's this one, that's the element with the smallest power here of all those elements in your H, your subgroup H. Alright? So if we can prove that these two are equal, we've got the proof, because we've shown then that all the elements in this subset can be generated from one element, A, and we suspect that that element is G to the smallest power here. See, that sounds plausible, because the generator here is the first one here, with the smallest power. In this case, 1, right? Just G, and we generate all the others by powers of 1. Well, this is a subset, so G, it's possible the G of here, G1, might not belong to H, might be outside, might be here somewhere. It's possible. Okay. So let little m be the smallest one, but it doesn't. It's not necessarily 1. It might be more. Okay. So let's try to prove this. Now, how to prove it? So we're sort of halfway there already, right? At least now we've got a direction, and that's often the hardest part in a pure math proof. Is how do you start? What do you do? So you have to think, right? In many ways, doing pure mathematics is like a continuous IQ test, right? I kid you not. All right. So how to prove that? I'll jog myself a little. There'll be quite a few steps in it. Now, a general element, like this one, right? A general element of this set will be of the form G to the big N, let's say. Okay, here, got that here. And we're thinking about G to the little m, the smallest one, and n is like the general case, so G to the n. Well, if this subgroup is cyclic, then all of these elements will be of the form G to the n. Well, they are all of the form G to the n because they're members of G. Okay, that we're trying to show that this general form is in fact a power of A. We're trying to show that G to the n is some power of G to the little m. Follow that? Because if it is, then any general member of this subset is some power of this. And that's what a cyclic group is. Right? So let's try to prove. So prove n is equal to something of that form. Right? Okay. So let's now So we're trying to relate big N and little m. Or we can say x here is of the form a to cube, some integer. So any element here is of this form. It's just some power of the generator, A. That's your suspicion. A is the generator of this subset. Alright, so let's try to relate A and M and try and prove this. So let's use the division algorithm we keep using. It's very useful. Okay, so N will be of the form Qm plus R, a remainder, the division algorithm. And R, you'll remember, the remainder, the residue, is less than M. Okay? So, let's see. Now, G to the little m, that was the smallest one, the smallest power in this sub, that belongs to H. Right? And that implies that G to the m raised to the qth power, q is an integer here, it's an integer, also belongs to H. Can you see why that is? This is just a member of this subgroup or group. So any power of it also belongs to the subgroup. Right? And why is that? Because it's closed. Right? It's a group, so therefore it's closed. So if you binary operate this with itself, the answer is in the group. If you binary operate it like the cube of it, again it's in the group. So if you do it to the q times, it's still in the group. Right? So this belongs to H. Now if the whole thing, if that belongs to H, its inverse also belongs to H because it's a group. H is a group. So its inverse also belongs to H. Okay? So now G to the n, that was just a general one of these members of H. G to the n belongs to H. Okay, now we can start using this and this. We can combine them, and we get the following. So G to the r, from r here, r is big N minus qm. Okay, so we can rewrite this as n minus q little m. Okay. And we can rearrange that slightly, so that becomes G to the n, G to the minus qn. And we can rearrange that a little bit, so it becomes G to the n, G to the m, q, minus 1. Follow that? Now look, this G to the m to the q to the minus 1, which is just the same here, belongs, this and this belongs to H. This belongs to H, that belongs to H. Okay? So you have a binary operation between this and this. Therefore, so you can deduce that belongs to H and this belongs to H. So therefore this belongs to H. So G to the R belongs to H. Right? So we've proved that this belongs to H. Right? Now what is R? What is R? Here we know R is less than m. Okay? But we postulated that m was the smallest value. Okay? That belongs to H. So this A here, we define little g of little m to power little m as A. So m was the smallest power in this group. Okay? But now we've proved that G to the R also belongs to here, to this subgroup H. Okay? So but R is less than m, and m is the smallest positive power of little g in this set, except for E. So the only way this is compatible with this assumption that m was the smallest is if r is actually 0. Okay, so r that implies that R has to be 0. Hope you followed that. If not, you reel back. Okay, so R is 0. Now look, if R is 0 from here, n is just Qm. Okay, so that means e to the n is of the form, sorry, x to the n. So x to the n is just x to the qm, right? And that's just x to the m to the power q. But x to the m is a q. Now this x to the n here is sorry, g. X is g. It should be g. Okay. So an arbitrary member of this subset here, little x, okay, it's of this form. It's the generator to some power n. Big N is just Qm. We proved that because R is 0. And you swap the m and q around, you get this form, our g to the m. We assumed was a. We assumed that was the generator. And look, for any member of this subset H, call it x, right? Whatever x is, it's going to be some power of this, right? And we assumed that g to the m is the generator. We called it a. That was the assumption. But now we've proved it. Any random member of this subset H is of the form, the generator, that's A, which is g to the little m, to some power. So there it is, proved. Okay, next section will be problem solving.